Hi, everyone. Thanks for joining today. Looks like people are still coming in, so we're just going to give it one more minute and we'll get started here. All right, well, now that we're 2 minutes after start, I'll just get started here with some housekeeping while more people come in. Thank you everyone for joining today. Just note that this webinar will be recorded and we will distribute the slides and the recording by the end of the week. If you have any questions, please drop them in the chat or you can raise your hand. We'll try to answer as many as possible, but we can keep them towards the end if that's good. I think that is everything. So I'll pass it on to our presenter today, Chris.
Thank you, Kate. Welcome, everybody. Thank you for joining. My name's Christopher Salerno. I'm an energy engineer for Linkus. Today, I will be presenting the ET23SWG002 gas-fired heat pump water heating and combination system pilot, phase 2F site number 1. So let's go ahead and get into it. So this is our team. Today's presenter was supposed to be Crystal, but I filled in for her today. She was the project manager overseeing on the side of Linkus, and then also we have Stephen representing from ICF. And so here I am down to the left, and then we also have support from my colleague as well at Linkus, Janik. So that's the team that worked on this, and then we'll go into the agenda. So we'll go obviously into the intro of the project, go a little bit about the background, go into the key project objectives, and then go into the detailed M&V plan that was established for this project, then go into the baseline data analysis, and then into the results, which includes the system performance results after installing the gas-fired heat pump, and then talk about what's planned to follow on work, and then go into conclusions and recommendations based on what we have found. So a little introduction into the gas-fired gas absorption heat pump water heater. That's what the GHP stands for, if you're not familiar. So the study objectives really were to do a field testing of this in a domestic hot water, DHW, right here. Only application at a multifamily building in California. So these water heaters have been used in space, combination space and domestic hot water applications. So the aim at this was just to do a domestic hot water only application in a multifamily, obviously in California. And then also we wanted to address knowledge gaps pertaining to performance, cost data, and also market acceptance. Then the key findings, which we found from this or the key findings from using these is that the energy efficiency obviously is reduced natural gas consumption when using these gas absorption heat pumps in place of traditional boilers, and then also operational costs, reduced operational costs. And there's also the key findings as it is a practical benefits in terms of there's no need to have costly electrical panel upgrades for standard electric heat pump water heaters that require large amounts of electricity or a high power demand, sorry. And so these do not require that, and so they're ideal for retrofits. And so also what was in the key findings is the adoption barriers. So these are not being adopted, obviously, in California due to very limited field data. There's not really much clarity on what the actual implementation costs could be. And then also contractors are not familiar with this type of products or this type of technology, so they tend not to use it. So then we'll go the impacts of this technology obviously are supporting decarbonization goals and also a utility measure package. So there already is an SDG&E measure package aimed at multifamily buildings. However, it's very limited and it offers little incentive. So our goal here is to be able to support a more developed measure package to provide more incentives. And also the impact of this is to offer a scalable, sustainable, cost-effective solution for modern DHW needs to domestic hot water needs. So these gas absorption heat pumps obviously can be scaled up and down to be able to meet larger or smaller hot water heating demands. So, but the target of these obviously is larger demands to be able to target larger energy savings. And so a little bit of a background on what studies have been done, the limited amount of studies that have been done on this type of technology used for water heating. So these studies all have to do, and I want to note that they only have to do, or they pertain to space heating and domestic hot water applications. And so there's not really any study, there is no study that just gears to a domestic hot water only application. So NEA has a study conducted in Salem, Oregon, that concluded with 18% gas savings, COP of 1.06, and they concluded that it's ideal for mild climates. And so there's another study from the Atmospheric Fund, Toronto, Canada, that found up to 20 to 50% in reduction of natural gas savings and about 10.1 tons of CO2 reduction annually. And then CAC in California, relevant to where we are, they did not characterize gas savings, only they did find up to a 50% reduction in NOx and GHG emissions, with cost advantages for energy intensive industries. So geared towards large heating demands. And so the research really is limited, so there's a lot of gaps. And so this slide goes into the gaps, into the specifically using these gas-fired heat pumps in domestic hot water only applications. And so obviously there's really a lack specifically for moderate climates like California where space heating is minimal. So the target of this field study was to be able to provide data for that. And then also there were 5 key gaps that were identified listed here. So firstly, performance data, there's limited insights into domestic hot water only efficiency and savings, so not including space heating. And then also sizing and integration. So at the beginning of this, there was really little knowledge to know how to size these gas-fired heat pumps specifically for domestic hot water applications, and then properly integrating them into the system. And then the third would be maintenance requirements. It was really unclear since contractors were not very familiar with this, not at all used in California for this type of application. It's unclear about the reliability and what the servicing needs will be from the manufacturer or the contractor, servicing contractors. And number 4 was the cost and payback periods. It's really high initial cost with really an uncertain ROI since there's limited amount of field data to be able to back cost savings analysis. And so the 5th one we have identified at the beginning was the awareness and utility incentives. So as I mentioned before, there's limited promotion and really incomplete measure packages that don't provide enough incentive to be able to drive these this technology and drive up the adoption of this technology into the market, into the domestic hot water, specifically for commercial and multifamily applications. So next we go over to the objectives. So the key objectives of this was obviously characterizing energy savings from reduced gas consumption by installing a more efficient water heating system or retrofitting to make it more efficient. And so the second objective was initially to characterize the carbon emissions reduction from using less gas to meet the same level of service for the domestic hot water needs. And the third was performance validation. We want to be able to validate these gas-fired absorption heat pumps in domestic hot water only applications and be able to support more of these applications. The fourth would be market barrier mitigation. We want to be able to address the barriers that we found throughout the project and to be able to minimize those and increase adoption of this. Our approach really was, as mentioned before, is this field study, which was a field technology assessment at the customer site, specifically a site with really high domestic hot water needs. And we'll go into that. Is it very important that these systems be used where the gas-fired heat pump is running as much as it can to be able to base load, and so it reaches high efficiency performance, and so you're at the end of the day making the system more efficient. And so we target places with high GHW loads. So the technology and product evaluation, so kind of what we did to be able to, what we did to implement this field study at this site was, obviously we did an assessment at a customer site for a realistic performance evaluation. But firstly, we did was site qualification. It was a little challenging to find a good site where the DHW load was sufficient to be able to keep the gas-fired heat pump running as much as it can, but also finding sites where the central domestic hot water heating systems are accessible and can be easily retrofitted with these technologies. So as you may be aware, gas-fired heat pumps need to be outside. So being able to retrofit these into systems requires running piping to and from outside where you would install it in a location that is, meets codes that is appropriate. And so you need to be able to run the pipe to and from, depending on where that's at, and then take all those considerations into play. Does the piping need to be trenched? In the case of this site, there were two systems, and we'll go into it, that were separated by about 55 feet. So there was underground trenching that needed to be done for the piping. But really, site qualification is important to be able to obviously reduce the costs to retrofit this thing reasonably, and to be able to have a base load that serves the gas-fired heat pump, and then it achieves optimal performance. So after we found the site, the first site for this study, we did the baseline data collection. So we started to installed baseline monitoring MMV equipment, measurement and verification equipment to baseline and monitor the existing baseline boilers water heating system performance. So that consisted of inline turbine water meters, diaphragm gas meters, temperature probe sensors, and CTs, current transducers to monitor the power. And so those were all being logged real time on a minute level basis to be able to characterize the baseline that we have at that place, at the property. And so the next was once we had our baseline period established, we did our system integration or system installation, where we installed a gas-fired heat pump, controls, heat exchanger, a circulation pump for the closed water glycol loop for the gas absorption heat pump, and then also the auxiliary equipment that was integrated into the system to be able to retrofit and integrate the gas-fired heat pump into the existing system. And so we'll talk about how that was done in the next slide. And then after the system was installed, everything was set up and optimally running, we started our post-installation monitoring period, where we basically let the gas-fired heat pump trying to have it run as much as it can for a set amount of period. So we collected a pretty good better half of a year of data for this. And so the last thing after we were done collecting data, we did a performance comparison. Obviously the post-installation data versus the baseline, but also against like a traditional electric heat pump water heater, standard electric heat pump water heater that would be used instead of this technology. And so now we'll go into the MMV plan. This is kind of the diagram. I know it's kind of a lot going on here, so Up here, you can see there's 2 domestic hot water loops. As I mentioned before, this site has 2 different central systems that are outdoors, thankfully, which made it easy to retrofit with the equipment that we use for this project. But yeah, so one system is at 750 kBTU hour with a 115 gallon tank. It has a recirculation pump, a standard recirculation pump, and then the hot water supply. So these 2 systems were independent to each other during the baseline. They serve about roughly 35 units each. And so this is the other system. It's essentially the same thing, but it's a little bit smaller boiler capacity at 650 kBTU, still with a 150 gallon tank. And so here's kind of a legend to show all the points, the MMV points that were used in this system to be able to capture the net heat output. What I mean by that is the actual heat that is supplied by the boiler into the water out to the system. So you can see here we have the green temperature sensors, and then the kind of orangish M dots. Those are the mass flow meters or the water flow meters that we use to capture the inline flow meters to capture the water flow, and in order to calculate what the heat energy is coming into the system from the cold water, in from the system from the recirculation load, and then out from the supply, hotline supply, which we call DHW supply, which is the hot water going to the attendant. So this is hot water going to one side of the property and the other side. And so our baseline period, I guess I should have mentioned that because we're doing as much parameters as we can do to be able to characterize the performance of this is an option B, retrofit isolation, so all parameter measurement. And also our baseline MMV duration was a short duration, but it captured a variety of behavior from the system. So we have about 2 months of data here. Unfortunately, if you see here, here's what says is a rebaseline. Unfortunately, during our post period, one of the boilers failed. So they had to replace domestic hot water 1 with a much more efficient, I think it's still a Raypak boiler. But yeah, the system was changed out, obviously, so it had to be rebaselined with the newer boilers. So there's periods and dates right here where that rebaseline occurred. And so from that, we were able to build a baseline. And now into the post system where we integrated the GHP here, that's what this block is here representing the gas absorption heat pump. It's basically, it's designed to be able to supply supplemental heating for the cold city water. And it says here, makeup city water. That's kind of a term that was used internally. That really is referring to the cold city water that's coming into the system and replenishing the tank from the hot water draw. So what we wanted to do is be able to, preload or preheat the cold water coming into those boilers, essentially so that those boilers wouldn't have to warm that water up to replenish or refill the tank with hot water. So essentially, this gas-fired heat pump operates on a closed water glycol loop, as you can see up here in the orange, and goes to and from 2 separate individual plate and frame heat exchangers. And so these are plate and frame heat exchangers going to each system. And so the cold water will come in, obviously heat up to a certain point and then go back to the system. And ideally, the boilers would not have to turn on if this system is running efficiently and optimally. So that's ideally what the initial design of the system was. It didn't incorporate preheating recirculation load for simplicity, just to see, based on our initial measurements, it was assumed that this system should have provided enough load for these, but we'll get into later why it actually did not. So This is kind of the system dynamics here. One thing to note that these drawings aren't so great. They were done in Word, but they serve the overall purpose of, of conveying the system dynamics. And so here, it's obviously not to scale, and this should be represented by 55 feet away. So essentially, the gas-fired heat pump was installed next to the system 2 because there was space to allow for it. And so we had to run underground piping over underneath, around, I think, a carport, around one of the laundry room, which was in between the systems. And so that was one of the costs that was associated with this. So that's one of the key things that should be taken into consideration when trying to consider this as an application. Is it makes sense to retrofit it, and these are space limitations that are provided that would make it very difficult. They're costly, and so this system essentially is about 55 feet away, but it's using insulated underground piping. So essentially, this gas-fired absorption heat pump is supplying supplemental heat to both cold water going to both systems. So that was the key objective from this diagram. So the initial baseline before the rebaseline was initially, as we went over, the 750 BTU, kBTU, 80% efficiency, and then there was a 650 with the 83% efficiency. So standard Raypak boilers, high delta boilers. And so the key components obviously were the two, 115 gallon storage tanks. They were running on, both had recirculation pumps running at constant speed, and they were mostly operating with uninsulated piping and standard boiler controls, standard tank stat boiler controls. And so the initial baseline results from using the initial system yielded COPs, or system efficiencies, for system 1 only about 0.58, and then system 2 0.68. And so that overall was a baseline efficiency of 0.62. So relatively a lower efficiency than which was envisioned for the system. But unfortunately, we had to re-baseline due to the boiler being replaced. So it's a newer high capacity, or the high efficiency condensing boiler that was put in place there. So it definitely did improve the overall system. So there was, I forgot to mention that the other boiler was also replaced. However, it was replaced like for like. So luckily we were able to, and it was providing the same efficiency values after rebaselining. So we didn't have to alter anything there. But more importantly, the boiler that was replaced that improved the overall efficiency required rebaselining. So another important thing to consider here is, obviously you want to pick a system that is running well, has no problems. In our initial assessment, we did try, we spoke with property management to try to assess, is the system properly operating, and will it break down or anything like that. But according to them, they didn't have any problems up until we still started this project. So that did require a rebaseline through summer, July of August, and then to the fall. So we did get some warm weather data, including into November, which was some colder weather data, which is kind of important. So it actually is very important. So when you're rebaselining, you want to be able to get a good weather coverage. So we've tried to get some hot weather data and then some cold weather data to be able to see if the performance is closely related with the outside air conditions, or the OAT. What I mean is the outside air temperature. And so the rebaseline performance, system 2 actually, even though it was a much newer boiler, the system efficiency only went up to about 0.75 due to the system dynamics and the system design in itself. So the overall system CLP only went up from 0.62 to 0.67, but it was important to be able to characterize that for any efficiency gain analysis in that we'll be talking about shortly. And so here we basically tried to characterize or find a relationship between COP and OAT. So COP is the coefficient of performance of the gas absorption heat pump, and then we have the OAT is the outside air temperature. So this is measured weather station data, typically from CalMac, that we pull in to be able to see, is this is the COP of the system, is the performance of the system, efficiency of the system tracking with the outside air temperatures, being that is the outside air temperature affecting or making it or affecting the performance of the boilers to be able to meet the same demand, assuming that the hot water demand is independent of the system that is providing that. So the initial baseline, we obviously expected that there would be some correlation between the system COP and OAT, but however, as you can see here, there is not really any relation. And we're just seeing system 1 here, but the same can be shown for system 2. It kind of is just scattered. Didn't really show any real strong linear relationship. So unfortunately, that did not find useful in our analysis. So what we had to do to be able to project annual consumption, gas energy consumptions, is we found that the gas energy input tracked very well with the net heating output. And the net heat output is defined as the difference of the supplied hot water energy between that minus the return, the hot water return and cold water energy entering the system. So basically the amount of heat the boiler is putting into the water and outputting. So we found, obviously, since the net heat output tracks very well with the gas energy input, we can use this to be able to project into an annual consumption, to be able to see how much this baseline would consume over a course of a year. And so the reason that we did this and the why we did this is we assume that the domestic hot water needs or loads will be the same regardless of the input system. So the tenants will be still using the same amount of hot water. And so that should be independent of the gas energy input, regardless of what system is using to meet the needs of that same level of service. So fortunately, we were able to collect baseline and post for about a year. So we were able to collect the actual net heating output of the domestic hot water systems for the baseline post for a year. So then we were able to use this equation here for the baseline, which uses the rebaseline, to be able to project what the gas energy input would be projected into the post. And so that gives you a yearly estimation. And so you can see that all the criteria met: good R squared, low CV, RM, SE, and then very low and a net mean biased error. So just going to provide a little bit of the installation pictures. So you could see here before the installation, you can see this is all new fencing. The existing foundation was here. Originally, this was an enclosure in itself. This is system number 2. And you can see here that there's the standard Raypak boiler. There's the 115-gallon tank. But you could see there's additional piping here for our flow meters as well. So we have all our M&V equipment in there as well. So you can see the initial step in this installation was obviously doing the concrete foundation, since the area which we selected for this did not have an existing foundation for that. And so you can see here that this is a nice concrete foundation with a little gate. And so this is in the middle of an apartment complex. This is the laundry room that I was talking about, and the other boiler system is on the other side of this laundry room. So you can just imagine there's like a pool right here, and then on the other side of this building, there's essentially the same exact system. And so to be able to integrate, what we did was we ran piping down through here into the ground and around the building to be able to integrate with the other system. So up here at the top left, I want to kind of go in order now. Sorry, I went out of order. was the installed gas absorption heat pump itself. So you can see here, this beautiful unit right here. It's on the concrete foundation with the buffer tank behind it. I think this is a 80-gallon buffer tank. And so that was sized appropriately to provide enough water glycol mixture into this loop to provide enough heat transfer for this unit. And so, yeah, so you can see here that the system is being integrated, and then the piping here is kind of how we integrated the heat exchanger to preheat the cold city water going into the system. So you can see here, following the red dot, the cold city water will come in. Actually, there's a pipe behind that. It'll come in. You can see right there, and then it'll come out heated back and go back to the boilers. This is the water glycol mix that's going to and from the gas absorption heat pump. And so you can see here we have our flow meter. We have a pressure gauge to maintain. We have a circuit setter here to maintain equal flow to both systems, as you want to be able to have equal flow to both systems, and then balance the heat, the mass balance the flow on the heat exchanger to maximize the efficiency of the heat exchangers. And so down to the lower left is the GAP or GHP, the DDC controller that was used. So it's operating on a basic DDC controller. And then we already went over the new concrete pad down to the right. So that's kind of a little bit of an overview of how we integrated the system. Obviously, since this is outside, it made it a little easy for us to be able to come and just, insert the unit here and then kind of start piping everything in. This is a very important consideration to take in if considering this application, obviously. And so let's go into a little bit of the challenges, the M&V challenges, and also the low water pressure issue. So initially, the design for the system, there really wasn't much support from the manufacturer, and the contractors that supported us also were not sure about how to properly design these. So they obviously struggled with heat exchanger sizing and buffer tank size. So the heat exchangers that you see that were shown wrapped up in the installation, unfortunately, were sized too small, and they only reached, from our data, they only reached up to about an average of 40 kBTU per hour. And so 2 of them adding up to 80, that in our gas absorption heat GHP is about 125 kBTU. So obviously it's only gonna be able to transfer a portion of the total energy. So it's not going to be as efficient as was initially envisioned for this. So also they struggled with, doing a proper buffer tank size. It took them initially they didn't know, exactly if they needed a buffer tank or not, and how much is sufficient or not, in finding, sourcing a reasonable amount, a low cost tank for that purpose, if it were only just 20 or 30 gallons that would be needed. Fortunately, here we needed at least 80 to 100 gallons, so we used an 80-gallon tank. So also there was also challenges with the controls. The manufacturers had 2 controls, so it was a little unsure how the contractors didn't really know initially how to set it up. The instructions that came with it were a little unclear, according to the contractor, from their experience. And so it took them, because they're not familiar with the product, it took them a little bit to figure it out what was needed for the installations. And so that delayed installation longer than was expected. So, right. So the site-specific challenges, unfortunately, there was low water pressure that arose when we started doing our baseline. As you can see here, this is a hose bib up to, I think, system 1, and it's only showing, it's hard to see here, but it's only showing about a little bit over 30 psi. And as you may know, that's a very low pressure, especially for a large central system. Typically, pressures should be ranging at least 40, 50, 60 to maintain proper flow, to maintain, and then also old check valves that fail. So the low pressure was causing weird system dynamics, such as reverse flows and lines that which should not have been reversed. But also another big challenge here was obviously in California, we have a huge hard water problem. So you can see here, this like almost, what is it? By scale here, that's like almost 3/4 of an inch of just calcium scale that build up in here. These are spinning turbine meters, obviously. So that this calcium blocked this thing up, and it wasn't outputting. It was being clogged, and it wasn't outputting, giving data that was making sense. So we had to come and replace this. And the only way that we knew that it needed replacement was opening it up. So that's another thing to note. These type of flow meters are they're easy to work with. They don't require power. They're reliable in the sense that if there's, not hard scale going through it, they provide reliable results. However, to get around this would require, say, like a much more expensive magnetic or something that doesn't require moving parts, that uses sound waves or something that doesn't require moving parts. And so, but those meters have their own problems. They're complicated to set up, calibration and everything else. So these come, freshly calibrated. You just have to install them, plug them in, and they pulse and give us our water flow meter. So it's the reason why we tend to stick towards using these more simple, cost-effective turbine flow meters. And then lastly, obviously, was the boiler failure. So there were several things that arose during this project that resulted in delays and just things that need to be considered in the future to be able to prevent these things, such as building bypasses for these pipings. So if, say, a flow meter does fail, you can just have it on a bypass, and then you can just close off the bypass and essentially swap in and out these meters, because these meters really they're threaded by unions, and then once the piping is installed, really swapping them in and out is really not difficult. It requires low effort. But I shouldn't say that. It's not very complicated, and it's doable. And so we want to go into the actual post analysis and kind of what we found. Or so here, what we try to do is try to fit a model for the actual GHP COP. And so fortunately, since we know the heat pumps are directly related with the OAT, since they exchange heat with the outside environment, we found that the GHP alone, its performance tracked well with OAT, but also the NHO as well. So we found that it was necessary to use OAT outside our temperature from the nearby weather station, and NHO, which is that net heat output, basically what the boilers are supplying to the system. And so that's how we were able to fit. We found a reasonably good fit at a 0.78 R squared, 19% CVRMSE, so a pretty tight spread, and then obviously the 0 and net mean biased air. So it meets all the criteria. And so in the baseline, if you remember, we really just used the net heat output to determine what the baseline consumption here. Here we're using the gas absorption heat pump, or the equation here, using net heat output and OAT to be able to predict the performance of that. So I also want to point out that the runtime of the GHP largely affects the COP, and so we'll talk about that in a couple slides. So here is actually the post system gas input. So this is the system that I showed on the previous slide with the GHP integrated. And so this gas input considers the input to both the boilers, but it tracks the input to the actual GHP itself. So, but the output of the system is the same, since it's receiving the same input from the return cold water, and then it's still supplying the same hot supply energy. So essentially you're only inputting now an extra factor of gas, which should be much more efficient ideally. These were analyzed on hourly levels. We collected them at minimum level basis, but we analyzed it hourly. And so You can see here that the post system was also related to the OAT and the NHO, the net heat output, and the OAT, outside air temperature. And so we were able to use this equation to project what the post installation gas energy input would be for a whole year, and also what it would have been in the baseline. Since we've collected and measured the net heat output, which should be independent of the system, since it's providing the same level of service, the same heating demand to the properties. And obviously OAT is independent of gas energy input because it's the weather, and that should be independent. However, it's directly affecting it. And so try to go a little faster here so we get through these. So this is the performance distribution. So what I said before is the runtime is very important. You want to be able to maximize the runtime for these GHPs. So here what you see on the top graph in the blue dots is the amount of times that the minute frequency is the amount of times it reaches that runtime frequency, or the runtime minute. So around 3,000 times it reaches, up until about I think it was about 17 or 10 minutes, and then it starts to drop off. The average overall runtime is about 17.9. However, you can see here that the COP, once the runtime starts to drop off, that's when the COP starts to reach above 1. So unfortunately, you can see here that our GHP was not running on average more than 17.9 minutes, and so it was only reaching a weighted COP of about 0.75. And I should back up and say that these orange lines that you see here are the COP. So on the right hand side is the axis for the COP. Right here is about 1 COP, so efficiency of 100% efficiency. And so you can see here that after the GHP reaches about 20 minutes, it maintains for the most part above a 1 COP. So that really kind of stresses the importance of keeping these GHPs running more longer. And the reason why this wasn't running as long as it should have been is because the undersized heat exchangers, and also the domestic hot water load going through the cold water wasn't enough to be able to meet the load of the gas-fired absorption heat pump. So it does not reach about steady state COP. It kind of, jumps around. And so this is due really to the gas pulsing meters that we use for these. And so we really just need more data at this area and these longer runtimes, since we don't have much data. We need more data at these long runtimes to be able to average out and find more steady state performance. The gassing pulse meters work in a way that they pulse when a certain amount of volume goes through them. And say that pulse doesn't happen until a minute, the next minute, the next data logging minute. So then most of the gas came through the last minute or hour, but then you logged it in the next hour. And so there's a little bit of an offset between that and the net heat output, because the flow meters work in the same fashion, but they're pulsing a lot more. So we have higher resolution of data. So really what we need here is to be able to get more data of these things running more than an hour. And so, yeah, so what we have, the impact of runtimes, which is less than 20 minutes, really significantly reduced the COP. And so the metering pulse calls, the vacillations in the minute pulse data after 60 minutes, and energy savings are highly sensitive to runtime duration. So it's really, really critical to maximize performance of this and keep it running based on the design and properly sizing these things to be able to keep them running and base loading them. And so that they're not just cycling up till about 20 minutes and turning off. And so these units really need to run for at least 20 minutes to be able to reach that optimal performance and then keep running. So this is the overall saving summary. So the energy savings here for the baseline versus the post. So At the end of the day, since the system really didn't reach a high COP, we only saved about 134 therms, which is about 4%. Another reason for that, so initially we projected that it would save at least 30%, but actually it was only 4 due to system design and what we went over the runtime limitations. There's also several things that we identified which could have been done differently. Obviously, the recirculation water reheating, the water coming back from the recirculation pumps is being dumped into the tank, so the boilers are still having to work to heat up that water, which is coming back, I think on average was about 100 degrees to about 105 degrees return temperature. And so obviously, even just warming up the cold city water from 60 to about 120, 130, you're still going to have that recirculation water coming back and requiring that to be heated as well if you don't want the boilers to be working as much, if at all. So the next thing, the challenge identified, and kind of the next steps that we're planning on doing is incorporating the recirculation load into this. So another challenge that was identified here was the site screening tools. That initially there was not really any. We used the ASHRAE site screening tool, but it accurately predicted the minimum heating load, and so that led to the longer short times, and then also the small heat exchangers didn't maximize the performance of the DHP when it was running. So a few things there, which led to the shorter run times from the design. So yeah, obviously the future improvements, we want to get that recirculation load. We're incorporated into there by directing the recirculation and the cold water to an IST, an indirect storage tank. And so so instead of using in this project that we used a standard plate and frame heat exchanger, instead we would use an indirect storage tank to improve runtime. So what would this do? This would allow the tank to cool off to a certain temperature before the GHP would have to turn back on and then bring it back up to temp. And so it would essentially be cycling less and then ideally be meeting more of the demand, essentially, and increasing the runtime of the GHP. That's the ultimate goal of this. But lastly, what we want to do as future improvements is as well as optimizing control settings to the GHP runtimes and efficiencies. So right now, the GHP really just has a standard tank stat on the buffer tank and the water glycol loop that it has. So that's basically telling the GHP to turn on and off. So there's obviously areas to improve on that based on more advanced controls to be able to control the behavior of the GHP a little bit more. So just a few more slides. This is the follow-up work. Obviously, we kind of went over this, the integration of the recirculation load, the IST. Our goals are increasing the runtime for fire efficiencies. And then another goal, we want to be able to validate lab data against the field conditions. Unfortunately, since this didn't reach optimal performance, optimal performance in itself, so then it was infeasible to validate against the lab data, which was reaching performance, obviously, for the lab conditions, lab environment. So the field studies, the future studies we have. So we have this study, and then we also have a hotel studied in Southern California. So we have installed another one with the IST design in a hotel in Southern California. So that's ongoing. Then we have another multifamily site that's slated for installation, and then we have another large hotel in Southern California that's going to be soon in the design process for that as well. So we're excited about that, to be able to learn what we've learned from here, to be able to integrate and optimize and really get a lot more savings and show valuable data from this. So the insights from the labs and field studies. So we really want to optimize site selection for sufficient DHW loads. So we want to, enhance the system design. So really, it's really important to select, as I said, low sites that have sufficient load, or else it doesn't really make sense to use these. So these are really targeted towards multifamily, a larger multifamily or commercial domestic hot water heating site applications. And so at the end of the day, unfortunately, from what we found, the COP only increased from 0.70 from 0.67, which was our re-baseline, which only resulted in 134 therms, which is 4% savings. And so, the biggest challenges, as I mentioned, contractors really didn't know much about this, expertise and gaps in design installation. There was really insufficient manufacturer support, specifically with the specific GHP that we selected. That has not been the case for the other equipment that we installed. But specifically for that, during this design process, the manufacturer did not provide any direct support. So it was kind of on the contractor themselves to be able to figure this out. So obviously there was some shortcomings there. So the short run times was limiting the steady state efficiency. So obviously that's the next goal, is to increase that runtime. And the next steps is to enhance that system design at that existing site. So we have in the plans to be able to go back and re-optimize and redesign, repipe, and then do what we integrate the recirculation load with the IST, and then ideally try to get this gas-fired heat pump taken on most of the base load, and then see higher efficiencies, hopefully. And then also next steps, what we want to do is be able to train contractors on these really. They're really not, they don't like to work with things they're not familiar with. And so obviously if they're familiar with these types of things, then we can start pushing adoption. And then also you need to train them on the site selection. So it's really hard for them to know. They think the sites are good, but we need to provide them with tools so they can determine if these sites are good. They provide sufficient DHW loads and such as that. So I think that's very important for us to be able to provide that for them, based on what we found here and what we're going to be finding in these next projects that we'll be presenting to you in the future. So the leveraging the findings to improve the GHP adoption. So yeah, we want to leverage what we found here to really push this thing in the utility profiles, and push a measure package, or to push more incentives to be able to get these really pushed into the market, and then really get things moving with GHP. In terms of DHW loads, so domestic hot water loads. So, right. So that was really the conclusion of kind of what we went over. Hopefully I left a little bit time for some questions, but definitely feel free to email Kate and or somehow get to me or to Crystal, the project manager, and we'll be able to answer your questions in a timely fashion if I won't be able to right now.
Hey, Chris, this is Ava Donald speaking. I'm also
Sure.
the program manager on the GET program. So if anyone has questions, feel free to email me too.
Sorry, Ava, I should have mentioned you too. I guess you weren't on the initial slide since you joined the team after this, yes. But
yep,
yes,
no
Ava
worries.
Donald. Yep.
Yep.
Yeah.
So.
And dropping email in the chat for any questions.
Unless anyone wants to unmute.
Yeah, if anyone wants to ask any questions, I can unmute you. Just raise your hand or drop your question in the chat. All right, well, looks like we're not getting any questions in the chat or any hands up. So yeah, once again, looks like we got a question here actually. From Michael. Chris, can you see that?
Yes, I could see it. So it's more of
Okay,
a comment. Cool. Some from Michael. Hi, Michael. Thanks for joining. Seems like with properly sized IST buffer tank, small loads would be also okay. aka build up with larger load with or to and from the GHP. Yes, I do. I agree with that. Yes, Michael, that is correct. But yeah, but I think initially when we're targeting larger loads, we want to target more savings, and that's what I meant by that. But of course, yeah, with proper system design, we think that yeah, these systems, a properly sized IST and or buffer tank and proper controls, will be able to mitigate the low efficiencies meeting smaller loads such as that. So that's kind of what we want to be able to address in the restructuring or the re-optimization of this project. So we're going to be going back and redoing that again. So, right, yeah, I do agree. That is a valid statement, though, Michael. I realize it's probably a lot of information, so feel free again if you think about this later. If there's anything that comes up, we'd be happy to answer any questions. I know it might be a bit too much to swallow, and then hopefully you guys will be looking forward to seeing the future presentations as well, because we will hope to present some more valuable results in our future projects upcoming.
Yeah, thank you, Chris. And if anyone goes to our website, cagastech.com, we have our calendar for the rest of the year for the webinars, so you can feel free to register for those. But if you're here, you're probably on our email list, so we'll send out the invite for the next one. But with that, if we don't have any more questions, we can go ahead and end the webinar. Thank you so much for your time, Chris.
Thank you, everybody.